In this video, I just want to go over the our Taylor Polynomials activity that I gave at the end of class today. Some of you were able to start on it, some of you weren't. But I just want to go through the activity so that you'll be able to do the homework for Tuesday. So first I want to explain this kind of complicated looking formula here. So this is basically what we found in the lab, that the nth Taylor polynomial, we constructed it for e to the x, and then we also looked at it for sine of x. But you have f of a, and then the derivative evaluated at a over 1 factorial times x minus a, then the second derivative over 2 factorial times x minus a squared, third derivative over 3 factorial x minus a cubed, and so on, all the way up to the nth derivative evaluated at a divided by n factorial times x minus a to the n. And this is just kind of a restatement. It's kind of a short way to write this. So notice that, like when j equals 0, I end up with f to the 0, which you can think of as just kind of the function, the 0th derivative. In other words, we haven't taken the derivative, we're just still dealing with the function. So f to the 0 is just f of a, 0 factorial is 1, and then x minus a to the 0, that's also just 1. So that gives us back our f of a term. Then, with this notation, we let j equal 1, and we have f prime of a over 1 factorial, x minus a to the first, then j equals 2, and this sum means that we move this index so we get 0, 1, 2, 3, and so on, but then the summation here indicates that we add these. We add up each of these terms as we go. So we generate the term with the index and then we add them all up. That's what that means. So here they're asking us to find the Maclaurin polynomial, which is just the Taylor polynomial when a is 0. All right, so it's centered at 0, just like what we did in the lab. We found the Maclaurin polynomial for e to the x and for sine x, because in both cases we were centered at 0. So we actually found this, but we're going to find it for cosine in two different ways. First, we're going to use this definition up here. So and then we'll talk about how to do it the second way. So we have that f of x is cosine x. All right, so f of 0 is 1. F prime of x is negative sine x. So f prime of 0 is negative sine of 0, but sine of 0 is 0. Now for the second derivative, take the derivative of this. The derivative of sine is cosine. This negative stays there, so I have negative cosine of x. So the second derivative evaluated as 0. Well, cosine of 0 is 1, so that's negative 1. Move this up here a little bit, because we have a few more to go. The third derivative, well, the derivative of cosine is negative sine. Tack that negative on, and we get sine. And that means the third derivative evaluated as 0 is 0, because sine of 0 is 0. Now the fourth derivative is the derivative of sine, which brings us back up to cosine again, right? So the fourth derivative at 0 is going to be the same actually as the function at 0, which is 1. And then similarly, the fifth derivative will be the same as the first derivative, right? This is going to be negative sine. So the fifth derivative is negative sine. And we already know that that's just going to be 0, because sine of 0 is 0. Okay, so we need those because we need the function value here, we need the function or the derivative at 0 here, the second derivative is 0, the third derivative is 0, and we're going to keep on going all the way out because this is degree 5 out to 5. All right, so we want to write T5. Even though this is Maclaurin, it's centered at 0, and that'll be obvious because we'll have an x minus 0. So let's just write this out before we simplify it. So the first term here is just going to be 1, because that's f of 0. And then plus, if we refer back up here again, the derivative at 0 divided by 1 factorial, x minus 0 to the first power. So that's this one. So that's just 0, right? Because the first derivative evaluated at 0 is 0, I'm going to have 0 over 1 factorial x minus 0 plus, now the second derivative evaluated at 0 is negative 1, so negative 1 over 2 factorial x minus 0 squared plus, now the third derivative is here, evaluated as 0, so it's 0 over 3 factorial x minus 0 cubed, plus fourth derivative at 0 is 1 over 4 factorial x minus 0 to the fourth, plus, and then the fifth derivative evaluated at, whoops, that should be a 0, right? At 0 is 0 over 5 factorial x minus 0 to the fifth. Now clearly, if the coefficient is 0, that term we're not going to need, that term's going to be 0, that term's going to be 0. So we're left with 1, and then that's minus, and then 2 factorial is just 2, because it's 2 times 1. Of course, x minus 0 squared is just x squared. So I've got minus x squared over 2. And in this case, well, let's just leave it, maybe it's 4 factorial, but that's x to the fourth. So plus x to the fourth over 4 factorial. Well, 4 factorial is 24, so we'll just write it. So this is the fifth degree. Even though it just goes to the fourth, it's because the fifth power term had a coefficient of 0. So this is our Maclaurin polynomial of degree 5 for cosine. All right. Now there's another way we could have gotten that. We saw that in the lab we found T5 of x for sine, and we found that that was x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And that was when f of x was sine x, right? Well, we know that the derivative of sine is cosine. So the derivative of the Maclaurin polynomial of degree 5 for sine should give us the Maclaurin polynomial of degree 5 for cosine because of this relationship here. All right, because cosine is the derivative of sine, I could get the Maclaurin polynomial for cosine from taking the derivative of the Maclaurin polynomial for sine. So let's do that. Well, the derivative of x is 1, and then this is going to be minus. So we bring down the 3 out front, x squared over 3 factorial, plus, again, bring the 5 down out front, and then that's going to be x to the fourth over 5 factorial. So let's see if we can simplify that a little bit. Now remember that 3 factorial is 3 times 2 times 1. So those 3's cancel. And 5 factorial is 5 times 4 times 3 times 2 times 1. So those 5's cancel, and I'm left with 1 minus x squared over 2, right? 2 times 1, plus x to the fourth over 4 times 3 is 12, times 2 is 24, times 1 is still 24. And you notice that's exactly what we got for the first part. All right, so this is one thing that's nice, is that we can, polynomials, we can take the derivatives of them, we can take the integrals of them, that we know that the integrals and the derivatives always exist for polynomials. And so that's one of the things that's nice about working with polynomials and why it's nice to approximate functions using polynomials. Okay, now moving on to the next thing, we're going to see more of that here. So this says find the Maclaurin polynomial of degree 10 for f of x equal to sine x squared. And you're given this hint that we can substitute x squared for x in this sine x. So first, right off the bat, let's just say what the Maclaurin polynomial is for sine x. I'm just going to give you this. You could get this by basically continuing with, you can get, if you do a similar process as we did here, you can keep going and get, you'd have to go, but you can see that the same cycle is going to happen here, right? And we just kind of keep plugging in here. You could also use, GeoGebra and just find the 10th degree Taylor polynomial. And what you would find if you did that was that this is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial. All right? Now, you can also notice that, up here, this was our 5th degree, and there's this pattern going on, right? First, we have alternating signs. It's positive, negative, positive, negative, positive. And then there's this odd thing going on, right? And that's because if you kind of go back to what we did here, notice because of the way these derivatives work out, every other one of them is either going to be negative sign or sine. So we have cosine, negative cosine, sine, cosine, negative sine, and so on. And if we're expanding at 0, which is what we do in the Maclaurin polynomial, all those sine terms will just be 0. So that's why we have kind of the even numbered ones kind of drop out here. Okay, well, that is for sine of x. So if I want sine of x squared, then I just take T10 and I substitute x squared everywhere there's an x. So this is going to be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared, x squared to the 7th over 7 factorial plus x squared to the 9th, just the 9th, 9 factorial. And if we simplify, we get x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus x to the 18th over 9 factorial. So that is the 10th degree Maclaurin polynomial for sine of x squared. In the next problem then, they ask us to use this, right? So we've already seen this whole sine of x squared thing in the take-home part of exam 1, that we were able to use GeoGebra to find a graph of the antiderivative, but we can't find the antiderivative explicitly. This is another way that Taylor polynomials are useful, is because in general it's easy to take the antiderivative, or in this case like the derivative of polynomials. We just use the power rule or the power rule in reverse. So what we're going to do then is we're going to say that 0 to 1 of sine x squared, if we approximate sine of x squared with this, then this is going to be approximately equal to the integral of x squared minus x to the 6th over 3 factorials. I'm just going to leave the factorials as they are for now. Over 5 factorial minus x to the 14th over 7 factorial plus x to the 18th over 9 factorial. And we're going to take, that's going to be a dx. All right, so antiderivative, again, we're just going to add 1 to the exponent and divide by the new exponent. So that's going to give me x cubed over 3 minus x to the 7th, and I'm just going to multiply, 7 times 3 factorial plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial plus x to the, x to the 19th, right? Add 1 over 19 times 9 factorial. And this we're going to evaluate as 0 and 1. So you can put that in. We put in 1. You can see we're just going to get a bunch of fractions. 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial plus 1 over 19 times 9 factorial. Now these are getting pretty small. 9 factorial is a large number, and then we're multiplying it by 19. Plus these are alternating, right? Some of them are positive, some of them are negative. So this is going to be, it looks like it's going to be pretty small, right? And that's just for the 1, right? But notice when I put in 0 for x, that's just going to be 0. All right, so what I get here is, I actually did this in GeoGebra. You get approximately 0.45968. And then you can also do this same integral in GeoGebra and find the difference. Now I had to take it out to like 15 places of accuracy in GeoGebra, because actually these digits were actually the same. All of them were the same for this. But if you take it out to find the error, so the error is going to be the difference between the actual terms. That actual area under the integral and what we estimated that area to be using T10 of x squared, right, from up here. Okay, in absolute value. If you find that difference, it actually turns out to be on the order of 2 times 10 to the negative 9th. So an excellent approximation for the area under the curve from 0 to 1. Obviously, if we maybe the farther we get away from 0, if we go 0 to 2, 0 to 3, 0 to 4, that's not going to be as good because our polynomial approximation is centered at 0. So the farther we get away from 0, the worse it is. But this is pretty darn good. Okay, so that is the activity. I'm going to do one more video with a couple of examples of things that you might see in the homework.